So the simple example is simple because we're just going to use Newton's second law directly. Truth is like in any real homework problem or real problem as an engineer or a physicist that you would try to use Newton's second law in, it won't be as simple as what I'm describing to you. There's quite a lot more work to do before you even get to the step of where I start from in this example. So in this example, I'm going to ask, what is the acceleration of an object if the object's mass is 12 kilograms and the net force on the object is equal to 60 newtons? This is the magnitude of the force, but this is a force vector, so I'm going to include also that it is at 30 degrees north of east. So this is a vector here. It's a force vector, or it's a net force vector. The mass, you notice, has no direction. It's pure magnitude. So the mass is a scalar, and the acceleration is a vector. So pretty easy, straightforward application of Newton's second law. So Newton's second law says that the acceleration is the net force on our object. So the acceleration of our object is the net force on that object. It's a vector divided by the mass. So I'll just write it's 1 over 12 kilograms multiplying, so that's 1 over 12 is the 1 over m that's in front of the F net, and then F net is 60 newtons at 30 degrees, I'll put in parentheses, north of east. So these two things right here, 60 newtons and 12 kilograms, you can see that they have to be divided. So 60 divided by 12 is 5. And the units are newtons per kilogram. And the direction just keeps coming along for the right, 30 degrees north of east. I'll remind you what north of east looks like. So here are some compass directions. East, if north is upwards, conventional on a map that north is up, or that's how maps are oriented, or at least how the language on the maps are oriented in the northern hemisphere, yada yada. So actually east is towards the right. I think it's interesting to point out that when you put west and east, they spell we, not you, on a typical map that you see in the northern hemisphere. And of course south is down here. And the way you go 30 degrees north of east is you look at the of east. Here is east, and we have to go north of it. So this is the direction that's roughly 30 degrees towards the north side of east. So our force vector is this 60 newtons long arrow at 30 degrees north of east. All right, so here's the direction, and here's the magnitude of our acceleration. Our acceleration, quickly, you can say, has a magnitude of 5 meters per second squared, because a Newton per kilogram is defined as a meter per second squared. This is the SI unit definition of the relationship. So 5 meters per second squared, and then the direction of A is this 30 degrees north of east. So that's the direction in which our object will accelerate under the influence of that net force. So some quick extras. So let me make a few comments. So the first comment is the answer to this question, what is the acceleration? It's not here. It's actually here. This is the answer to what is the acceleration vector. because a vector has both direction and magnitude. This is not the answer. It's part of the answer, but it's not the full answer. So that might be the first comment, that acceleration is a vector, and you have to sort of be careful of what people are asking for. The next thing is, I gave you an interesting example that's using angle magnitude vectors. You'll notice that the acceleration has the same direction as the net force. The net force has this direction, 30 degrees north of east, but so will the acceleration. They'll never ever have the same magnitude though, and they can't because they're dimensionally different. This is a force and this is an acceleration. They're not even in the same physical dimension. You can convert this, of course, to thinking about unit vectors, which is honestly my preferred way of thinking about vectors. It's just easier. In my head, it's easier to do math. When you do angle magnitude stuff, you have to do trigonometry. But when you use unit vectors, the truth is you just have to add and subtract the different directions separately. So that's quite simple. Very quickly, it's interesting to point out that if you go and you re-understand your net force as components, so this is the net force in the x direction, in the multiplying the unit vector in the x direction called I hat, plus this is the component of the net force vector in the y direction, and then we multiply by the y direction, j hat, like this. You can actually just do a little bit of vector math. The acceleration vector, which is a sub x I hat plus a sub y j hat. This is the x component of the acceleration, can be a positive number or a negative number. Also here, y component, positive or negative, be meters per second squared, meters per second squared. These are newtons, can be positive or negative. But check this out. This is 1 over m, right? We're just going back up here. It's 1 over m times f net, where we write f net this other way. So f net in the x direction, I hat, plus f net in the y direction, j hat. These are multiplication dots. This is equal to, you can just distribute into the sum, right? It's a factor on a sum. So this is f net in the x direction divided by m times I hat, plus f net in the y direction divided by m times j hat, like this. This thing I just put a parenthesis around is a sub x. And this thing I'm putting a parenthesis around now is a sub y. That is Newton's second law. You can use it component by component.